Before HTTPS, when you submitted a login form on a website, the username and password traveled across the internet as plain text. Anyone with access to the network between your computer and the server could read it. Network administrators, ISPs, anyone on the same Wi-Fi network all could intercept your credentials with basic tools. This isn't theoretical. In the early days of the web, security researchers demonstrated strip attacks at conferences where they intercepted Wi-Fi traffic in hotel lobbies and collected thousands of credentials from unsuspecting users. The attack required no special hardware, just a laptop. TLS transport layer security was designed to prevent this by providing 3 guarantees for any connection: confidentiality, data is encrypted so eavesdroppers can't read it; authentication, you're actually connected to the real server, not an impersonator; and integrity, data hasn't been altered in transit. HTTPS is HTTP running over TLS. The S means the connection has all 3 of TLS's guarantees. Today, TLS is not optional. Google ranks HTTPS sites higher in search results. Browsers show not secure warnings on HTTP sites. Many browser APIs, geolocation, service workers, camera access, are restricted to HTTPS-only contexts. Users have been trained to look for the padlock icon. Beyond user-facing requirements, TLS protects your application itself. Login sessions, API tokens, database credentials sent between services all benefit from encryption in transit. TLS provides 3 distinct cryptographic guarantees. Understanding each prevents you from thinking, I have HTTPS, I'm secure, when there are other attack surfaces. Guarantee 1: confidentiality. The data is encrypted using symmetric encryption. AES is most common. The encryption key is established during the TLS handshake using asymmetric cryptography. Once established, all data is encrypted with a key that only you and the server know. An eavesdropper sees only encrypted ciphertext. Guarantee 2: authentication. TLS proves you're connected to the entity you think you are. This is done through certificates. When you visit myap.com, the server presents a certificate that says, I am myap.com, signed by a certificate authority you trust. Your browser verifies this certificate against its list of trusted certificate authorities. If the certificate is valid and the domain matches, the connection is authentic. What authentication prevents? Man-in-the-middle attacks. Without authentication, an attacker could intercept your connection, pretend to be myap.com, and relay traffic to the real server. You'd encrypt your data, but to the attacker, not the server. With certificate authentication, the attacker can't present a valid certificate for myap.com, because they don't have the private key that matches the certificate, so the browser detects the mismatch. Guarantee 3: integrity. TLS uses MAC message authentication codes to detect tampering. Every TLS record includes a cryptographic signature. If any byte is altered in transit, the signature doesn't match and the connection is terminated. Data arrives exactly as sent or not at all. The TLS handshake is the negotiation process that establishes a secure connection before any application data is sent. Understanding it helps you diagnose TLS errors and understand performance implications. Step 1: client hello. Your browser sends a client hello message to the server. This includes the TLS version the client supports, a list of cipher suites the client supports, the encryption algorithms, and a random number, client random, used later in key generation. Step 2: server hello. The server responds with the TLS version and cipher suite it selected from the client's list, its own random number, server random, and its SSL certificate. Step 3: certificate verification. Your browser verifies the certificate. Is it signed by a trusted CA? Is the domain name in the certificate, common name or subject alternative names, matching the domain you're connecting to? Is the certificate still within its validity period? Is the certificate revoked? If any check fails, the browser shows a security error. Step 4: key exchange. The client and server use asymmetric cryptography, RSA or ECDH key exchange, to establish a shared secret without sending it directly over the network. Both sides derive the same session key from the client random, server random, and the key exchange result. Step 5: session established. Both sides switch to symmetric encryption, AES, using the session key. All subsequent data is encrypted with this key. The TLS 1.3 optimization, TLS 1.3, the current version, reduces the handshake to fewer round trips, making it faster. It also improves security by removing older, weaker cipher suites. An SSL certificate is a digital document that proves identity. It contains the domain names it's valid for, the organization that owns it, the public key of the server, the certificate authority that issued it, the validity period, not before, not after, and a cryptographic signature from the CA. The certificate proves a specific claim, the organization named in the certificate controls the domain named in the certificate, and a certificate authority vouches for this claim. How the CA's signature works: the CA signs the certificate with their private key. Your browser has a list of trusted CAs, built into the operating system and browser. Your browser trusts a certificate if it's signed by any CA on its trust list. The browser verifies the signature using the CA's public key, which it already knows. Subject alternative names: SAN's modern certificates list all domains they're valid for in the SAN extension. A certificate might be valid for mmap.com, www.mmap.com, api.mmap.com, and staging.mmap.com simultaneously. Let's Encrypt issues certificates with SANs. Wildcard certificates, valid for star.myapp.com, covering all immediate subdomains, but not sub-subdomains. A wildcard certificate for star.myapp.com covers www.mmap.com and api.mmap.com but not sub.api.mmap.com. Certificate chain: your certificate is signed by an intermediate CA, which is signed by a root CA or browser's trust root CAs. The chain of trust goes: your certificate, intermediate CA, root CA, browser, trust store. Jinx must be configured to serve the full chain, not just your leaf certificate. Certificate authorities are the companies that issue SSL certificates. They verify that you control a domain, then issue a certificate saying so. Your browser trusts them because they're included in the browser's or OS trusted CA list. There are hundreds of CAs, but a few dominate. Let's Encrypt: free, automated, open certificate authority run by the Internet Security Research Group. Issues 90-day certificates. The leading choice for server certificates because of the free cost and automation. We'll cover this in detail. DigiCert: commercial CA, used by large enterprises. Certificates cost money but come with support and longer validity periods. Sectigo, formerly Komodo, another major commercial CA. AWS Certificate Manager: free SSL certificates for use with AWS load balancers and CloudFront. Can't be downloaded and used on non-AWS infrastructure. Cloudflare provides free SSL certificates for domains proxy through Cloudflare. The certificate is between the user and Cloudflare. You need a separate certificate for Cloudflare to origin traffic. Domain validation, DV, versus organization validation, OV, versus extended validation, EV/DV certificates, which lets Encrypt issues, only verify you control the domain, they don't verify the organization behind it. OV and EV certificates verify the organization. In practice, DV certificates are sufficient for most web applications. Modern browsers have removed the green address bar that used to indicate EV certificates. CA compromise: if a CA is compromised, all certificates it issued become untrustworthy. This has happened. DigiNotar was compromised in 2011, and all its certificates were revoked. This is why certificate pinning in CAA DNS records exist. Let's trace what happens at the network level with HTTP versus HTTPS to make the difference concrete. With HTTP, your browser connects to port 80 on the server. A TCP connection is established, SIN, ACK, the TCP three-way handshake. Application data is sent immediately in plain text. Get/login http:/1.1 host mmap.com, plus all the request headers and body, all readable by anyone in the network path. With HTTPS, your browser connects to port 443 on the server. TCP three-way handshake. Then the TLS handshake, 1 to 2 extra round trips. After TLS is established, encrypted application data is sent. An eavesdropper sees encrypted bytes. They know a connection to port 443 at a specific IP occurred, but nothing about the content. The performance overhead of TLS adds latency, the handshake round trips, and CPU overhead, encryption/decryption. Modern TLS implementations have optimized this significantly. TLS 1.3 reduced handshake round trips. Session resumption allows repeated connections to reuse a previous session's keys, skipping the full handshake. TLS false start allows the client to send application data immediately after sending its key exchange, without waiting for the server's confirmation. In practice, HTTPS is imperceptibly slower than HTTP for most applications. The security benefit vastly outweighs the minimal performance cost. Where TLS doesn't protect you, TLS encrypts data in transit. It doesn't protect data at rest, your database, protect against injection attacks, or validate that the server application itself is secure. TLS is one layer of security, not the entire security model. TLS termination is the process of decrypting HTTPS traffic so it can be processed as plain HTTP. Understanding where this happens in your stack matters for both performance and security. In a typical Node.js plus Nginx deployment, Nginx terminates TLS. When a user makes an HTTPS request, the encrypted request travels from the browser to Nginx. Jinx decrypts it using your SSL certificate and private key. Jinx then forwards the decrypted HTTP request to node.js via proxy_pass on localhost 3000. Node.js never sees TLS, it only sees plain HTTP. Why terminate it in Jinx? Node.js handles TLS poorly compared to Jinx. Jinx is built in C, handles TLS with OpenSSL or boring SSL, extremely optimized libraries, and manages concurrent connections efficiently. Node.js is JavaScript, TLS and Node.js works but at significantly higher CPU cost per connection. The traffic from Jinx to Node.js is localhost traffic, it doesn't go over the public internet, so encrypting it isn't strictly necessary. It's on the loopback interface, which is only accessible from the local machine. Security consideration for multi-server setups: if Jinx and Node.js are on different servers, e.g., Jinx on a load balancer, Node.js on back-end servers, traffic between them should also be encrypted. But for a single server setup, localhost communication is inherently private. Cloudflare TLS termination: if you're using Cloudflare proxy, Cloudflare terminates TLS on their edge. Traffic from Cloudflare to your server can be HTTP, flexible SSL, or HTTPS, full strict SSL. Use full strict mode requires a valid certificate on your origin server. This gives you TLS all the way from browser to your server. Let's look at what a complete HTTPS Jinx configuration looks like and why each part matters. The two-server block pattern: for HTTPS, you typically have two server blocks. The first handles HTTP, port 80, and redirects to HTTPS. The second handles HTTPS, port 443, and does the actual proxying. The HTTP redirect block, server, listen 80, server_name mmap.com www.mmap.com, return 301 https:// This permanently, 301, redirects all HTTP traffic to HTTPS. The 301 tells browsers and search engines to update their bookmarks and cache the redirect. The HTTPS block, server, listen 443 SSL, server_name mmap.com www.mmap.com, SSL_certificate/etc/let's encrypt /live/myapp.com/fullchain.pem, SSL_certificate_key/etc/let's encrypt /live/myapp.com/privkey.pem, include /etc/let's encrypt /options SSL jinx.conf, SSL_param/etc/let's encrypt /SSL params.pem, location /proxy_pass http // localhost 3000 proxy_set_header host proxy_set_header x real IP proxy_set_header x forwarded for proxy_set_header x forwarded proto. The x forwarded proto header is critical. Node.js needs to know whether the original request was HTTP or HTTPS, since it only sees decrypted HTTP from Jinx. This header tells Node.js the original protocol. Even with a 301 redirect from HTTP to HTTPS, the initial HTTP request is still vulnerable. A user who types mmap.com without https:// makes an HTTP request first, which then gets redirected. An attacker who can intercept that first HTTP request can redirect the user to a phishing site instead. HSTS HTTP Strict Transport Security solves this. It's an HTTP response header that tells the browser, for the next n seconds, only connect to this domain using HTTPS. Never try HTTP. How it works: on the first HTTPS visit, your server sends strict transport security, max age equals 315360000, include subdomains, preload. The browser stores this policy. For the next 31,536,000 seconds 1 year, the browser automatically upgrades any HTTP request to HTTPS before making the connection, even before any network traffic occurs. The HSTS preload list: browsers ship with a built-in list of HSTS domains, sites that should always use HTTPS, even on the very first visit, before the browser has ever seen the HSTS header. To get on this list, submit your domain at hstspreload.org. Requirements: redirect all HTTP to HTTPS, serve valid HSTS header with max age at least 1 year, include subdomains, and preload directives. Warnings about HSTS: once you enable HSTS with a long max age, you're committed to HTTPS for that duration. If your certificate expires and you can't renew it, browsers will refuse to connect entirely, they won't fall back to HTTP. Make sure certificate renewal is automated before enabling HSTS. Adding HSTS in Jinx: in your HTTPS server block, add _header strict transport security max age equals 315360000, include subdomains, always. A scenario that tests understanding of TLS's authentication guarantee. A user visits https://mmap.com. A man-in-the-middle attacker has positioned themselves between the user and your server. The attacker has a valid SSL certificate for evil-attacker.com but not for enyap.com. They attempt to intercept the HTTPS connection. What happens? Option A, the attack succeeds because HTTPS only encrypts the data, not the connection itself. HTTPS doesn't just encrypt data, TLS's authentication guarantee verifies that the server presenting the certificate actually owns the domain enyap.com. Option B, the attack succeeds because the attacker has a valid SSL certificate. Having a valid certificate for evil-attacker.com doesn't help with attacking enyap.com. Certificates are domain-specific. Option C, the browser detects the mismatch between the domain in the certificate, evil-attacker.com, and the domain being visited, enyap.com, and shows a security error. This is correct. TLS's authentication guarantee requires the certificate's common name or subject alternative names to match the domain being visited. The attacker can't present a valid certificate for enyap.com unless they've compromised myapp.com's certificate or the CA. Option D, the attack succeeds if the user ignores the browser's security warning. Technically correct as an edge case, if a user clicks through a security warning, the attack could proceed. But the browser would display a large, scary security warning. Modern browsers make this very hard to dismiss for HTTPS errors. The answer is C, TLS certificate authentication is the defense against man-in-the-middle attacks. The attacker needs a valid certificate for your exact domain, which requires either compromising the CA or stealing your private key.